Testing. Okay, hello. Can you all hear me? Now, you need to open up the chat because I want to hear from you guys at home as well that you can hear me. So just give me a moment and then I'll turn off the camera. Chat, here we go. Can hear you. That's great to know, Chris. Thanks so much. So I'll put this in a location where I can kind of see this and what I'm doing over on the doc cam. Now, tell me, do you guys see what's on the, do you see my hand? Just put a yes or a no in the chat, if you would. Great, good to know. Okay, I think we're set to go. So I'm just gonna turn the cam off. All right, good, that'll give us some more space. Now, it was a bit of a complicated setup, so we needed to start a little later today. Looks like we're only 1 minute behind schedule, which is not too bad. Two computers to set up with a document camera, so this will be a little bit different from the previous sessions because much of what we're going to do today will be document camera work. So I'll be doing some pen and paper calculations and talking about your assignment in MATH7502. So I hope that's what you're here for, MATH7502. Okay. All righty, so you have an assignment 1 of 2 assignments, and of course you have other assessment too, but this will be very important to you. So let's explain some of these questions, all right? So I hope to not do too much of these questions, but more to explain and to talk about some mathematical definitions that might help you through it. Okay, so if you have any questions, just stop me midway and ask that. So we're gonna have a little bit of a go of trying to do some Julia 2, but that won't be very much. It'll be mostly for the sake of me learning to master using 2 computers at once. Okay? But that's important because occasionally we'll need to be able to do that. All right, so let's have a look at this first one. Now, it says, consider the system of equations. So what we have are 3 equations and 3 variables, x, y, and z. All right, so eventually we're going to want to solve this, but the first problem says represented as AW equals B, where W is equal to x, y, z. Now that looks like to the power of t, but it means transpose. Remember that most of the vectors that we deal with will be column vectors, but yet it's convenient to write some of them in rows. And when we do that, we put a t to mean to transpose that. All right, but you see it fits nicely in the row and in the line here, so that's why we write it that way. Okay, so I'm not going to do this question, but I'm going to say, let's invent another one that's much like it so that I can do some of the calculations. All right, so I'm just going to write down one that I've copied down earlier to make sure that it worked. So instead, let's consider 2x plus 2y is equal to minus 3z plus 4, one equation. And it looks like I might have to shift the chat a little bit. Just give me a second so I can not cover too many things up. All right, now another equation. Let's just write something like this, but not the same one. 4x is minus 5y minus 6z plus 3. And how about 7x plus 9z is equal to minus 8y plus 5. Okay, so let's represent this as AW equals B. All right, now what we want to do is put all of the terms that have a variable in them on the left-hand side and all the constant terms on the right-hand side. Okay, so in that case, well, I'll write that 2x plus 2y plus 3z is 4. And now I want to match that with a corresponding row of a matrix equation. So I'll just start to do that at the same time because I don't want to take too long on this. All right, so I'm going to write it in this form. I'll put the x, the y, the z there, and on the right-hand side, I want the right-hand side of all the constant terms of each of these equations. So that would be, in this case, 4, 3, and 5. All right, now what I do on the left in my matrix, now this will be a 3 by 3 matrix because we have 3 variables and 3 equations. What we do is we read off the coefficients of each of those when they are on the left-hand side. So that's 2, 2, and 3. Okay, then we have 4, but when we take the minus 5y and the minus 6z over to the left-hand side, well, we have a 5y and a 6z, and so we'll write 4, 5, 6. Now you see a nice pretty pattern here. That's because I wasn't feeling very creative. I started with 1, 2, 3, 4, 5, 6, 7, 8, 9, but that matrix had a 0 determinant, which wasn't useful to my purpose, so I then had to change and make the first one a 2, okay? All right, so we've done that if this were the same problem, but it's not the same problem, okay? All right, now what is the b in this case? It's the right-hand side. So this here is the b. This is the w, all right? But of course, you might want to write that as a row. And then this here is the matrix A. Okay, good. Now let's have a look at the second part of this question. Solve for W numerically in Julia. Okay, now I'll write what we're meant to do in this case. I'll just write the code, okay? Now there's probably, we probably need to write using linear algebra first, okay? But the code would be, I would just enter the matrix A equals, right? And then I would put A slash B. Of course, I need to put B in memory too. Okay, now this is an exercise for me. Can I work both this computer and the computer that has Julia on it? Okay, so I'm going to stop screen sharing now, and I'll screen share on my other login on the other computer and do this in Julia. Right, it's not touchable. I have to get the mouse out. Okay, sure. All right, can you still hear me? Scooted over a little bit, but I'm a little bit farther away from the microphone. So now I'm going to screen share on the other computer. Okay, great. Do we see this one? I think we do. What about you, Walla? Do you see the one with Julie on it? Yeah. On your screen at home? Okay. All right, so what I'm going to do is just use old code that we considered, I think, in the first week to do this, all right? So I believe I would go using linear algebra, so Shift-Enter there. And now I'm going to change this matrix to be 2, 2, 3, and then 4, 5, 6, and 7, 8, and 9. Okay, and I'll put that into memory. Great, that works. Now I want to enter B. So B equals. Now I know B should be a column vector. Okay, but let's see if I get this entered correctly. So 4. Now I want a semicolon here. Put a space, then a 3, semicolon, and then a space, and a 5. Shift Enter. Great, that looks like what I was expecting. Okay, next I need to calculate the solution. So then I write A slash B, Shift Enter, and I wait a little bit. And great, it looks like I have an answer. So let's read that answer as 3 minus 5 and 2.6 recurring. Okay, great. So now I'm going to stop sharing here and I'll go back to the doc cam. All right, great. Okay, are we back? Walla, does that look all right on your screen? Are you logged in to Zoom? Okay. All right, so back to it. So we've done the second problem, and I hope that was successful, but I'll find out when I look at the recording later. All right, so the next one says solve manually using Gaussian elimination. Okay, so what I'm going to do, rather than me write all of the details, because there's a lot to write when you do such a problem, instead I'm going to show you some calculations that I did earlier on that by hand, okay, with this particular problem. All righty, so we've already got our system here, AX equals B. And so what we want to do is write a, what's the word for this? Well, I can concatenate A and B and form a new matrix. Okay, and it looks like what I have right here. All right, so in other words, on the left, we have the matrix A, and then on the right, I have the column vector B, and now I perform by hand Gaussian elimination on it. So in other words, I'm doing row-reduced echelon form as a Julia function, right? That would be RREF, if I remember right, where this is the matrix I would input as the input of that function. But again, this is a hand calculation. So now what I like to do is retain integers wherever possible in such a calculation, right? And that's the way that I minimize the number of errors I make, because I'm not a computer, I'm a human, and so I have a tendency to make arithmetic errors. So I want to minimize those. And so one way to do that is to try to maintain integers if you can. All right, and so the way I do that is in my row operations, you see, here's an example. What I've done in the first row is I've multiplied that row by 2. So I have 4, 4, 6, 8. And the reason I've done that is because I want the number that's in the position in the first column and second row, I want that to be a 0. So I want to be able to subtract these two. Okay, so that's why I've done that way. But then later I'll go back and divide throughout by 2, and I'll write this row here, the original top row. Okay, so now I can see after having done that what I want to do is take row 2 minus row 1 and make that the new row 2. All right, because I'll get a 0 there, I'll have a 1 there, and that'll be very nice. Okay, so that's the next step. All right, but you see that while I'm at it, what I do is I return the original row, which is simply to divide that first row by 2. Okay, so I've undone that operation. All right, so this is good because I now have a 0 under what would be the first pivot. Okay, so now I have to do the same. I have to get rid of this 7 because I want a 0 where that 7 is. Okay, so I do the same thing. So that would be to multiply the top row by 7, multiply the bottom row by 2, and then take their difference. All right. So here we go. That's the next line. Now I have a 14 in the front. All right, but still I can do all of this with integers. And so now I can see I probably want to subtract the first row from the third row and make that be the new third row. All right, so I should have a 0 in the bottom left and a 2 in the next entry. Okay, so there we go. We have that. So we have a 2 in the next entry. And those operations continue in all of the entries there in the same row. All right, so, and you can see also that I've again divided by 7, so I have the same first row as I had earlier. Okay, any questions so far? I seem to see that the chat has gone away on my screen, so I hope you're still there. Well, I wonder if you could operate the chat and just let me know if there's any question. Because I don't want to muck around with the computer for fear that I stuff something up at this stage when it's been working so nicely. All right, so next, now that we've got zeros under this main pivot, we want to get a 0 under the second pivot that we have now. Okay, now many people would go and divide this first row throughout by 1. If you like to do that, that's perfectly fine, right? But you're going to introduce a fraction there at the position of the 3 when you do that. I like to avoid those because I find it easier to do arithmetic on integers. All right, now next we want to, let's see, what have I done? Oh, well, that was an easy step, right? Because I can just do a subtraction. I can use the second row to subtract from the third row. So in other words, I can multiply the second row by 2 and then subtract and have a new third row. And that's quite simple. I've got a 3 and an 8 and zeros to the left of that. Okay, so we're nearly there, right? We have now, the left-hand part of this is upper triangular. So we're almost there. We just need zeros above our pivots if possible. Okay, so we only have 1 now to deal with, that 3 up here. And this is easy because all we have to do is subtract the third row from the top row, and we're basically done, other than doing our divisions. Okay, so next we'll do just that. We'll make that subtraction, first row minus third row, and that's now the first row. Okay, so now we have something diagonal here, right? If you just look, it's diagonal. Okay, so that's great. We can see that this is an invertible matrix A. Now all we have to do is divide by these numbers that are on that diagonal. Okay, so the first one is simple, divide by 2, and I get 1, 0, 0, 3. And then the third one, well, there we have a fraction, so 3/8. Okay, all right, and I'll show you that. So now you see we have the identity matrix there on the left, and we have our answers on the right. All right, so this is the solution that we got in Julia earlier, if I hope it is anyway. I don't have it written down, but I remember there was a 6 recurring. Okay, who knows? Who knows? Maybe I entered it wrong. Anyway, so I think I did this calculation correctly. All right, so we get W is equal to 3 minus 5 and 8/3. All right. Now, let's have a look at some of the other questions here. Need to be mindful of the time, too. Okay, and we need to accelerate it a little bit. Now, the next one, so we're up to looking at D. Find A inverse explicitly using Gaussian elimination and use it to manually obtain W via W equals A inverse B. Right, now if you had A, W equals B, algebraically you just multiply by A inverse on the left and you just get this equation, right? A inverse times A is the identity matrix, and the identity matrix times W is W. So that's why we get that. Now, how do you do this? Find A inverse explicitly using Gaussian elimination. So I'll just describe the process. All right, but I'll tell you that you can do the other part at the same time. So you could do both C and D at the same time. All right, now let's just talk about doing D. So what we would do is write down the matrix 2, 2, 3, 4, 5, 6, 7, 8, 9. And then over on the right, what I want to do is put the identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, now row reductions. there'll be quite a few. I won't show you those, but when you do row reductions on this, what you'll end up with eventually, once you achieve the row-reduced echelon form, you will have the identity matrix on the left when your matrix A is invertible, and in this case ours is. I don't know about this one because the one you were given, I'm not going to tell you whether or not that's invertible because that's your job. All right, so what we get is 1, minus 2, 1, and minus 2, 1, 0, and then 1, 2/3, minus 2/3. Okay? So that's what we get when we apply the Gaussian elimination process to this matrix that I've invented. Okay, together with the identity on the right. So you perform Gaussian elimination, you eventually get the inverse, the identity on the left and the inverse of the matrix A on the right. Have you got any questions? Now, this is all entirely elementary, but it does take some practice, right? You've got to learn about row reduction, so you may not all be familiar with that. So I suggest that you do some practice, and you'll definitely get some practice by doing this assignment. Okay, so let's move on now. All right, so next one. This says, consider two vectors, u and v, and they're in R3. So that means that these vectors are columns with 3 rows. All right, so 3 entries, they're column vectors. And now it says, let A be U, V transpose. And if you're not totally familiar with that, you might think, oh, that's the dot product, but it's not, okay? The dot product would be the other way around, or what you might know as the inner product. And that's because we're looking at column vectors here. Okay, so this is, and so I'll just write it out. So this would be A equals, now let's just say let U be U1, U2, and U3. And let's let V be V1, V2, V3. But if we transpose that, then we have a row, V1, V2, V3. Okay, so this is actually a 3×3 matrix when you multiply this out. So let me just do one or two of these entries, okay? So, okay, we've got a 3×3. Now that would be U1 times V1. And then we would have U1 times V2, and so on. I'm not going to do any more of that because that goes too far, because this is just to explain some concepts of your assignment. All right, but what I would suggest to you to do is once you do multiply that out, have a look at the rows and columns and their relationships to one another. Can you do any, say, row reductions on an associated matrix? Okay, just think about that. I think this will be quite an easy problem once you get to it, right? Okay, so let's move on then, because I think that's easy enough, and I doubt you have any questions, but if you do, just speak up. Okay, now the next one looks a bit scary, but it's not too bad. And I think, if I remember correctly what Yoni said, I think Yoni said that he might have done some related problems in his lecture. Does that sound right? Maybe? Okay. So you might want to go back and listen to Yoni's lectures and get some more hints on this. But let's see what I can do without giving anything away. All right, so let's look at 3A. Consider two vectors in Rn, so think of those as column vectors with n entries. Present proofs for the following. Okay, so the first one is the norm squared of u plus v. Okay, and then there's the right-hand side. You've got to prove that those are equal. Now, I'll just give you a hint, okay? So the hint will be put or use the identity that the norm squared of the vector x is equal to the vector x transposed times x. All right, now typically when you're writing maths by hand, you would put a tilde under these to say that those are vectors and not just single variables, right? But you'll find with this course, and maybe it's a stats thing, but very often just the letter X with no tilde and not even bold, that would represent a vector at least in this course, but I don't know if it's a stats thing. Maybe it's a stats thing to do that. All right, so when you see that, think about the context. It probably means a vector. It might mean a scalar though. So again, think about the context of your problem. All right, so here's your hint. Now, if you did that with this problem, right, and then expanded, you'd basically be done very quickly. Okay, so I don't want to say much more about that. All right, now how about the next one? All right, so the next one is, it looks similar, all right, except this time you start with what would be the right-hand side of this. All right, so I'll say this is a hint to do the next one, but you need a couple other hints as well, such as that x plus y transpose, where those two are vectors, is equal to x transpose plus y transpose. So you want to use that. And we're not done, okay? So the next one, you would want to use the identity that x transpose y. Now, since these are x and y are column vectors, x transpose y in this case would be a scalar. Or you could think of it as a scalar, even though it's really a matrix with one entry, but think of it as a scalar. All right, but this is equal to y transpose x. All right, so those three identities should be quite helpful to do 3B. Okay, let's have a look at the next one. Cauchy-Schwartz inequality. Now, I have a feeling that this is one that Yoni would have done in his lecture, but I could be wrong, so I don't know. I haven't watched the lecture. But it's a bit more involved, okay? So this would be probably the most involved one of this problem set of three. Question 3, that'll be the most involved one. But it's not too bad, right? And there are several proofs of it as well. So you more or less could just get on the internet and look for a proof, but if you do that, please put it in your own words and make sure you understand that proof, okay? All right, so one that I saw that I thought was fairly nice and easy to follow was one where you would introduce another vector, say z equals u minus u transpose v over norm of v squared multiplied by v, right? Because this here will be a scalar, that's a vector, that's a vector, that's a vector. And the task would be to show that z transpose v is 0. And that would be helpful because you could write a triangle, a right triangle, something like this. Okay, and then you could use Pythagoras' theorem on the vectors. Okay, and once you had done that, you'll get the sum of two squares, right? And then when you have the sum of two squares, you can say that the sum of two squares is greater or equal to something else because squares are positive or zero, right? And so that's easy. In other words, let's just write some numbers. 2 squared plus 3 squared is greater or equal to 3 squared, all right? So you could do that with this. All right, now the lengths in this case would be norms. All right, but if I say much more about that, I would be completing the problem. Now, I suggest you go through the details of your favorite proof of this. Write enough English in each of the steps that say what's going on, right? Don't just write mathematics. If you can write some English, please do it, okay? So to explain the steps, how you go from one step to another step. Do you have any questions about this? Anything in the chat? No? Are they still there? Are you guys still in the chat on Zoom? Just give us a thumbs up or a yes or a no. Yes? Oh, good, Walla. Are they in there? Yep, okay, great. All right, so let's move on. Now, so the rest of these, I'll just say they're easy. Okay, you might not agree, but given that you've done the first three, say, the rest would be easy because you can then use one of, say, the first three to do the rest of these. Okay, so the triangle inequality, for example, you could use, okay, I'll just say hint, use A and C to get the triangle inequality out. But again, you could find that out on the internet, and quite possibly Yoni's done this as well in class, okay? So likewise, the next couple you could do with previous ones, okay? So I think it's time to move on to another problem to talk about, okay? So let's have a look at question 4. Okay, find two 3x3 matrices with all non-zero entries that commute. Now, what I'll say is that this is an exception to the rule, right? So in general, matrices don't commute. In general, AB is not equal to BA, but sometimes they are. All right, so this one is very easy. So I'm not going to give you any hints on that. It's very easy. Do you agree? Yeah, you just have to get creative. Okay, let's look at the 5th question. All right, so this one involves a couple of definitions. So I'll have to pull out something that I've printed earlier. And I'll cover up what I've done on the problem, but we'll just do a little reading of it first. In chapter 3 of VMLS, so that's one of the books on, or one of the recommended texts for your course, there are definitions for AVG, RMS, and STD. There's also a derivation of this identity for any vector x. STD squared is equal to RMS squared minus AVG squared. Describe the steps of the derivation of this formula in detail. Okay, so I'm going to show you a piece of that book where the derivation is, all right? And I'm going to show you the definitions, these 3 definitions. All right, here we go. So, all right, now AVG, as the name suggests, that's the average of the elements in the vector x. So the sum divided by n, where n is the length. Okay, now RMS. that's the sum of the squares of the entries, and then you take the square root. So in other words, that's the norm of the vector, but dividing by the square root of n. Okay, now STD, I think that's standard deviation, right? Yeah, good. I see some nodding heads. Yeah, that's great. So I don't often deal with standard deviation, unlike Yoni. It looks familiar to me as a standard deviation, but I could just say something dumb and it might not be. So I'm good to see that it looks like it is, right? So great. Okay, so that's standard deviation. X is an n by 1 matrix. So I point that out because, well, it's just a column vector, right? But it might help you think about the way everything's set out, okay? So there's a derivation, basically, of this identity, and it's right here, okay? So that's part of that book. So let's have a look at it. So it says STD of x all squared is equal to this. So that's the opening line. So we have 1 over n, that's a scalar. Then we have a square of a norm. Okay, so this is a formula written in terms of vectors. All right, so here we have a vector x, and then we're subtracting. That's a scalar there, right? Divided by n, and then we have another bold 1. All right, so what do you think the bold 1 means? Well, you're probably thinking to yourself that, of course, it means the column vector 1, 1, 1, dot, 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 1, 1, 1. So it's the column vector full of 1s, okay? But, well, I didn't always know that, okay? So you may not know that either. Now, so this first term after the minus sign, that's 1 transpose. Now, 1 transpose will be a row vector or a 1 by n matrix. And then, as we know, x is a column vector, so an n by 1 matrix. So this product, 1 transpose x, well, that's a sum, isn't it? So that's the sum of the entries of x. So that's what that does. It just adds up the entries of x. And then, so that's a scalar, and then it gets divided by n. All right, so I'm not going to talk about every line of this, but what I'm going to suggest to you is that you do this in 2 ways, okay? So I would suggest to you that you take those definitions up here, which involve sums, and you do the calculation showing that these 2 are equal using sums, right? Because in that way, I think it's straightforward. And your task then is to relate your proof involving sums to the proof here that involves matrices or vectors, I guess. Okay, so let's have a look at the what you're meant to do. Describe the steps of the derivation of this formula in detail. Okay, so that means put in some English for each one of these lines and probably write this out yourself rather than copying and pasting what's there, and then explain what every term is and how each line is obtained from the previous one, okay? I don't think it's very difficult, but it's an exercise because, as I know, this book, one of the nice things about this book, what did the code go? VL something. VMLS, the book does a lot of these statistical and calculations via linear algebra, which is pretty nice. For example, I mean, if you just look at that, that is expressing the standard deviation in terms of the norm of a vector, okay? So that's pretty nice. All right, so that's all I'm going to say about that one. And it looks like we're at 10 to the hour, so I had better hurry up and talk about question 6. Okay, so question 6 says, do exercise 3.26 from page 67 of VMLS. All right, so I got that one. So I'll just write it here. Oh, you can see I'm not writing it, I'm just putting it. Okay, so this is just basically a screenshot of that question, but let's have a look at it. So time series autocorrelation. Suppose the vector suppose the t vector x. Okay, so let's just pause there. What is a t vector? So that means that this column vector x has t entries, uppercase T entries in it. It's a non-constant time series, okay? So that's a new and fancy word, but this is just, you can just think of it as a vector with T entries, where those entries have meaning. Maybe you could think of it as the price of corn over time, for example, or the price of your favorite thing over time. All right, so now with little x subscript t, the value at time or period t. So this is just a mathematical way in this context to index from the vector x, okay? So that's the tth entry. All right, sure, so mu. Now mu is just the mean, and this is in notation we've already seen. So here we again have the bold column vector 1. So the column vector with 1s in it, transposed times x, and that's divided by the length. Okay, so you clearly see that's a mean. So the autocorrelation of x is the function r of tau, defined for 0, 1, and so on. Tau equals 0, 1, and so on, as the correlation coefficient of the two vectors. Okay, so I'll stop there and I'll point out, because me not being a statistician, I'm not totally familiar with those terms, so I had to look them up, all right? But what I should have done is looked up within this book itself, all right? Because they may be different than you were expecting. All right, so you have a peek at my next page. So, all right, so this one has a particular definition. So I'll just explain this in words first. So here we have a round bracket x, and then we have mu times the bold vector 1, but there's a subscript tau there. So mu 1 subscript tau. So that is the column vector with tau entries in it, where every entry is equal to mu, because that mu is a scalar that gets multiplied by that vector. So every entry is mu, and it has length tau. Now this vector x has length uppercase T. All right? Now you might think that this is the inner product, the dot product, right? But not in this text, it doesn't refer to that. What it refers to is well, I want to say concatenation, but it's not quite, right? So what you do is you just take the vector x, and on the end of it, you glue on this vector mu1 subscript tau, okay? So in other words, you just join the two vectors to make a new column vector of length t plus tau. Does that make sense? And so in this one, this is the same operation, but where mu times 1 subscript tau is in the front. So it starts with several mu's, and then it ends up with the entries of x. Okay? Sure. So the other one was the correlation coefficient. Now that is defined in the book also. Okay, so I'll show that to you without showing too many answers. And I'll have a peek at the time. Looks like we've got 2 minutes, and I'll have to rush out and get a drink of water. All right, so what we have here, so that's what that concatenation, hang on, it looks like this. And I think I'm showing possibly too much there, but what I want to point out is here is your definition of rho, okay, which relates to r of tau, your function. Now that's important, so you need to go and find that in this VMLS book, okay, and relate it back to this. Now that's all I want to show you, right? This is a rather involved problem. It'll take you a while, but I don't want to show you any more of those details. Okay, and that's all for this session. So I'm going to do all of this over again in the next hour, but meanwhile I'm going to go grab a drink and get organized, okay? All right, thanks guys. Thanks, guys. See you next time. What's that?
Yeah, I have new five U1T. Yeah, 1T means we have each one, we have one numbers of one tau, yeah?
Yeah.
Yeah. Mu is constant, yes?
Mu will be constant, yeah, because it's a mean.
Yeah, so we have a vector. The is mu as well. So they
Yeah, that's right.
All are constant. We have a new vector, which are constant.
Yeah. Yeah, so, I mean, things change when you do more calculations later, right?
Yeah.
Okay, it's 6, so let's begin again. You have a look at the chat. So if you're joining in now, welcome. So we're here for MATH7502, and we're going over some definitions, notation, and a little bit of problem solving in this, related to this assignment 1 of yours, okay? So what I plan to do is just go through a number of calculations. Some of these are easy, and some are a little bit more involved. But let's start by looking at this first question on your assignment 1, where it says, consider the system of equations. Okay, so we've got 5x plus 3y equals 2z plus 4. Now in that equation, you see some variables and you see some constant terms. So in this case, 4 is a constant term, right? We've got coefficients times variables. Now the first question says, represented as AW equals B, where W is equal to X, comma Y, comma Z transposed. Okay, so that's a column vector, but it allows us to express it as a row, so it fits nicely in the row or in the line of the text, right? So that's what that uppercase T as a superscript means. It means to transpose that so that that's a column vector. Okay, so I want to do a similar problem so I can show you some of the calculations involved, all right? So it's not the same one. And the problem I have in mind goes like this. So let's consider these 3 equations, which are different to the ones shown. All right, so we're considering 2x plus 2y equals minus 3z plus 4. 4x is equal to minus 5y minus 6z plus 3. 7x plus 9z is equal to minus 8y plus 5. And I want to represent it as AW equals B. W is like that. Okay, so you can see this is very similar to the one you're given. Now what we want to do is put all the constant terms on the right-hand side. I'm going to need to zoom out a little bit to fit more on the page. Okay, so I want all the constant terms on the right-hand side, and that will be basically the entries of my vector B. And then I want the terms that have variables in them. I want those on the left. Okay, but at the same time, I can write down a matrix equation, right? Because all I have to do is copy down the coefficients when they are on the left-hand side and put them into a matrix. All right, so let's go ahead and do this. So this here will be my matrix A, and then I will have a vector W, which contains X, Y, and Z, and then I'll have a vector B. And eventually we want to solve AX equals B. Okay, good. So now, if I were to do that with the first row, I would want to take the minus 3z over to the left-hand side, and I would have 2x plus 2y plus 3z is equal to 4, right? So the way I want to write this in a matrix form is I put the 2, and the 3 there, and over here on the right-hand side of the equation, as the first entry of B, I put my 4. Okay, next I have 4x, but I want to see that as 4x plus 5y plus 6z equals 3. Okay, so 4, 5, 6, and then over here I have a 3. And then in the last scalar equation up here, I have 7x, so I put a 7 there, but next comes a 9z. Now remember, we've got this minus 8y, which we take over to the left-hand side, and so we have 8 next. And then finally the 9, and then we can put that constant term, the 5 there, okay? All right, that's very easy, isn't it? Yeah, okay, great. But not everyone knows this, so. Okay, let's have a look at the next one. So solve for W numerically in Julia. Okay, so I've already done this in the last session, but just so that I can be in good habit of being able to swap screens with no drama, I'm going to do it again. but I'm still here. Okay, so I moved the mic over. Now you might need to increase your volume if you're at home, because I'll be a little bit farther away from the mic now. Okay, can we see this? Okay, I'll make it bigger. So what we do first is we enter using linear algebra. And next, we enter that matrix, but look at the notation. A equals square bracket. We have spaces between the entries and the rows, semicolon to separate the rows. And we can just shift enter that, and it goes into memory. Now the vector B that's on the right-hand side, 435, okay? 435, great. Okay, next, all we have to do is go A backslash B for shift enter. And here we get 2.99, but those 999s go on and on. And you can see that eventually we have a 6 in what looks like the 15th decimal place or so. That's a little bit odd, but okay. All right, now you can see this really represents the number 3, right? So we should note this solution as 3 minus 5 and 2.6 recurring. Okay, great. Any questions? So that's all we had to do with this one. Now, obviously, you've got to do that with your system, which is different than my system. All right, I'll stop screen sharing here, and I'll go back to the dot cam. Okay, and then I can move the mic over again. Okay, and I will pull up the chat so I can see it this time. Okay, great. So moving on, let's have a look at C, solve manually using Gaussian elimination. Okay, so I'm going to solve this one that I've written here manually using Gaussian elimination. Now, we already know that Julia told us that the answer is, Julia said that we have the column vector 3 minus 5, 2.6 recurring. Was that correct? I think so. All right, great. So let's keep that in mind. Now, I'm going to solve this system using Gaussian elimination, okay? But the way that I do it, I try to maintain in the entries integers as long as possible, right? And the reason that I do that, is to avoid the introduction of fractions too early, because when you have to introduce fractions in a hand calculation, it's, well, if you're like me, it's more likely to make errors, all right? And we don't want arithmetic errors. Because let's face it, fractions can be a little tricky, even though we all know how to add fractions, right? It can be easy to get to be wrong. Of course, you could do this with decimal numbers, right? But then you've got to go and punch in a calculator or a computer, or, right? So anyway, this is the way I do it. So step 1, take this system, put the matrix on the left, the matrix A, on the left of a new matrix, okay? Take the column B that's on the right-hand side, join that to the matrix A, in other words, concatenate the two matrices to form a new matrix. That's called the augmented matrix. Some people like to draw a dotted line or a line there. I don't think you need one if you know what it means. Okay, then you perform row operations on this matrix. In other words, what you're seeking to do is row reduce to obtain the row reduced echelon form. So in Julia, that's, I think it's RREF, is that right? Voila, RREF. It is in MATLAB, okay. Sure. Okay, but as I was saying, I like to keep integers in there. So what I'm doing first is multiplying the top row by 2, because I want to get a 4 in the top left entry so that I can get rid of this 4 by subtracting. I want to make that 4 a 0, right? So in other words, I multiply this one by 2, and then later I'm going to subtract the 2, because you see here, and we separate this by a tilde, incidentally, to mean that I performed a row operation on that to get this one. Okay, so I want to subtract row 2 between row 1 and row 2, but because I like to keep positive entries, if possible, in the front, I'll take that as row 2 minus row 1, and I'll make that the new row 2. All right, so I'll get a 0 there, a 1 here, a 0 there, and a -5. Okay, so that's the next step. But while I'm at it, I go back in the first row and I divide throughout by that 2 that I introduced earlier, because I don't really want that there in the end, do I? I want to keep it as simple as possible. Okay, so that's my next step. Now, I have a 0 under the first pivot, which is good. That's getting towards the goal of having zeros under the pivot. Okay, so now I need a 0 where that 7 is, and I'll make it look more like a 7. But the way I want to do that, now, of course, you could divide throughout by 2 and get a leading 1 there. You could divide this throughout by 7, get a 1, but you would have fractions, right? And if you're like me, you want to avoid them. And so instead, what I do is I multiply the top row by 7. I multiply the bottom row by 2. So I have 14s there. Then I can subtract 14 from 14, which I like better. Okay, so that's what happens next. So next we have multiplied the top row by 7. We've multiplied the bottom row by 2. And next we want to subtract. Did you have a question? No, good, okay. All right, so that's simple. Next, I want to subtract those, but if possible, I want to keep a positive number up front. And so I go 16 minus 14 rather than the other way around. So row 3 minus row 1 is the new row 3. Okay, so we perform that operation. We make that the new row 3. Now we have a 0 in the bottom left entry. So we have zeros under the main pivot, which is great. Okay, we happen to have 1 in the next pivot. So you see how there's zeros before that in that row? That makes that a pivot. Okay, and so we now want a 0 below this pivot, and then later a 0 above the pivot, but we'll make a 0 below the pivot next. Okay, so yeah, to achieve that, I'll multiply the second row by 2 and then subtract, right? But to avoid writing too many steps, I'll jump. So once I do that, right, having multiplied that by 2 and subtracted and made that the new row 3, now I have a 0 under my second pivot, okay, which is great. And if you look at this, now we have zeros below the diagonal. So this part of it would be upper triangular. That's great. Okay, so we're nearly there. We've got a 0 above the pivot now as well, because I've also subtracted the third row from the first row in this step. Okay, so I've done a couple of things there, operations to get to this line. And now lastly, we want zeros above the last pivot. So we want a 0 there, which we already have, and a 0 here. So all we have to do is subtract the third row from the first row. And then we're pretty much there, right? All we have to do next is divide, okay? So we've maintained integers so far, right? We have a 6 up here, so 2006. And then we have a 1 there, a 3 there. So if we divide so that our pivots are now equal to 1, we will be done, right? Because now this matrix here, when I cover up the last column, that looks a lot like the identity matrix. It just doesn't have 1s down the diagonal, right? So this is a diagonal matrix. It's just not yet the identity matrix, okay? So I divide the top row by 2, I divide the bottom row by 3, and that's great because in the top row I have 1, 0, 0, 3, and in the bottom I have 8/3, okay? But now that we have the identity matrix right here on the left, that tells us two things. It tells us that this matrix is, or the matrix A is invertible, right? And it also tells us the answer that we're seeking, right, which is this. So in other words, W equals 3 minus 5 and 8/3. And if you divide 8 by 3, you'll get 2.6 recurring. Okay, I guess there are no questions. Let me have a peek at the chat. Is there anyone in the chat, Walla? No, okay, right. But anyway, this is recorded, so if you didn't understand what I said in the first hour, you get to hear what I say in the second hour. Maybe I say it a little bit differently. All right, where were we? Let's have a look at the problem set. So next, find A inverse explicitly using Gaussian elimination and use it to manually obtain W via W equals A inverse times B. Okay, so the first thing let's notice is what's happening here is you have A, W equals B. You multiply on the left on both sides by A inverse. A, W equals A inverse B. Okay, whatever you do, don't put that A inverse on the other side because remember in general, these are not commutative. And in fact, if you did that, you get a different size anyway, right? Okay, so do it on the left. All right, now this simplifies, that's I, W. Okay, and IW, of course, is just W, and so that's why this works, all right? Okay, so how do we do this by Gaussian elimination? Well, what you want to do is you take the matrix A, you form a new matrix with it. In other words, you concatenate and form a great big matrix. So we had 2, 2, 3, 4, 5, 6, 7, 8, 9. That was our matrix A in our example. And then over here we have, we put the identity matrix. And we row reduce, okay? So when you're done, what you'll get is the identity on the left. And on the right-hand side, you will have the inverse of the matrix A. And in this case, this inverse is 1 minus 2, 1, minus 2, 1, 0, 1, 2/3, minus 2/3. Okay, what was I going to say? Oh yeah, you could combine the two steps, as in you could do C and D together just by including another column, right? So if you did that, that would give you not only the answer, but also the inverse of the matrix A. Of course, you have more work to do, but if you're going to do two Gaussian eliminations, it's less work to do, you know, one row reduced echelon form of a matrix, even though it's a bigger matrix. Do you agree? Great, good to hear. Okay, so now the final step would be to multiply this inverse times the vector B, and you get your answer, right? So should we do that? No? It's too easy. Yeah, I agree. Okay, but just in case, right? I don't know if you guys did the previous course, but did you do the previous course?
Not very wide.
No, but you did something else, which is probably just as good. Yeah.
Many few years.
All right. Well, welcome to the degree. All right. Okay, so let's move on. Now, next one, consider two vectors Fortunately, these are in R3. Okay, so you only have to have 3 entries in each of U and V. All right, so let's just choose some notation for this. So what we might have is, well, let's have a look at this first. A equals U, V transpose, okay? So if you're hasty, well, you know the saying, haste makes waste. So it's best not to be hasty unless you're really confident about being hasty, right? But if you're hasty, you might see that as the inner product. It's not the inner product, right? Because these are well, we're treating them as column vectors from the beginning, right? So I think just a convention for vectors in this course would be that they're column vectors. Okay, so let's now give some notation for U and V. So this would be A equals, say, U1, U2, U3. And then V, we could say, let V be V1, V2, V3. But if we transpose that, then we have V1, V2, V3 in a row, right? Now, this is a 3 by 3 matrix, right?
Yep.
If it had the other order, then you would just have a 1 by 1 matrix, which you could think of as a scalar, okay? But this is a 3 by 3 matrix. Now, I'll just calculate the first 2 terms of it and let you do the rest. Okay, so we have U1 times V1. And then remember, we deal with the first row of the left one first, right? Well, depending on how you do the matrix, in my mind, I do the first row first. So anyway, so U1 times V2 would be the next entry. Then there's an entry here, there's an entry there, an entry there, an entry there, an entry there, and an entry there, okay? I'll let you guys do the rest. Now, the question says, explain why determinant of A is equal to 0. So obviously, you could then calculate the determinant by hand, which would be symbolic, and that would be a reasonable explanation. But I think you can do better. Because you should just be able to make an observation about the way that matrix looks and come up with a good reason of why the determinant is 0. So that's all I want to say about that, because it's just about as easy as multiplying a matrix times a vector. And I don't mean that as those calculations are similar. Okay, so let's have a look at the next one then. All right, so here we have a bunch of things. So 6 different proofs to do. Okay, so that looks a little bit scary, but it's really not as bad as you might first think. All right, so don't fear. You should be able to get this one successfully. All right. Now that's not a guarantee, but it's not that bad. Okay, so let's have a look at the first one. So present proofs for the following. So this is in Rn. So these have n entries. So the first one is the norm squared of U plus V is that. Okay, so how do you deal with that? Well, I suggest to write down some identities. So let's just write down some identities which will help you prove all of these things, right? So now the first identity will be that the vector X transpose times X, this is the same as the norm of X squared, okay? And I'm intentionally not going to put a tilde under these because it's pretty common in this course to see a single X without it being bold or without it having a tilde under it, and that will mean, or it will often mean that it's a vector, okay? And the same letter X could mean a variable like it is here, right? So you have to determine what it is through the context of the problem. Okay, so this will be a great identity, and you can see how you could probably use it there, right? Okay, now let's consider another identity which would be useful for you in these problems. And that might come up in the next one. So for example, that X plus Y transpose is equal to X transpose plus Y transpose. And if you think about it, that's pretty clear why that should be the case, right? If you had, say, two column vectors, you added them together, the entry in the first row might be x1 plus y1. And so if you're transposing the resulting vector that's the sum of those, well, you're just writing it in a different, you're writing those in a different way, right? So, and then you can break them up again and you get this. Okay, now another identity that will be helpful is that X transpose Y. Now this one is not the same as that one because we're treating these as column vectors, okay? So this here is a scalar, or think of it as a scalar, even though that's a 1-by-1 matrix, right? But that would be the inner product. And of course, you can swap that around and say that that's Y transpose X, okay? So these are some identities which will help you do much of this problem here. Okay, now the next one, C, Cauchy-Schwartz inequality. So here we have absolute value of U transpose V less than or equal to the product of the norms of U and V. Right, now that one is a little bit tricky. I have a feeling, this is not a guarantee either, but I have a feeling Yoni might have done at least one of these problems in the lecture. And if I were him, I probably would have done the hardest one, which would have been this Cauchy-Schwartz inequality. But I'm only making a guess because I haven't watched that. Okay, so right, now there are a number of proofs of Cauchy inequality that you could find, right? You just browse the web, search Cauchy-Schwartz inequality, and you can find a number of proofs. So I had a look at some of the proofs, and one that I thought was easy to follow and simple enough to write down involved Pythagoras' theorem. So in other words, I want to find a right triangle. Okay, but so in other words, I want to introduce a vector z, and incidentally, I've seen this straight on Wikipedia, so it's probably still there. So introduce z equal to u minus u transpose v over norm of v squared. And I'm not going to write down the whole proof. I'm just going to give you some key features of it, okay? Okay, and then the first step is, once you've got that, now what we have here, this is going to be a scalar right there times a vector, right? So vector, vector, scalar, whole thing is a vector, whole thing is a vector, that's a vector. Okay, but what you would do in that proof is show first that Z transpose V is 0, all right? And what that would do is tell you that the vector Z and the vectors V are orthogonal. Okay, so you could think of this in terms of a triangle in n-dimensional space, right? But it makes a nice analogy if you just draw one on your page. And incidentally, I like proofs that allow you to think geometrically, right? Gives you an opportunity to, I don't know, wrap your head around it more easily, perhaps, right? Because you think geometrically and then prove algebraically, and it all fits together nicely. So Z, and then up here we have U transpose V. Okay, over norm of V squared times V, and then we can put U. All right, and now we can use Pythagoras' theorem on these three vectors, all right? And what that would do is it would give you a sum of two squares, right? But the good thing about squares is that you know for sure that they're either positive or 0, right? So then you can write something like this: a squared plus b squared is greater or equal to b squared. And I don't think many people would disagree with you, right? Okay. That's all the hint I'm going to give you on this problem, okay? Because there are ample proofs out there. Whatever you do, write it in your own words in a way that you understand, Okay, don't copy anything. And give enough details. All right. Now the rest of these problems in question 3, well, most of them you can use some other identities above. Okay, like for example, A is a very useful identity that you could use down below. So we have the triangle inequality, we have the parallelogram law, and Pythagoras' theorem, okay, involving norms of vectors. So each of these can use something above, right? But I want to give you a chance to properly think about this and properly do a good exercise on this, so I'm going to stop giving hints on that. All right, let's have a look at question 4. Meanwhile, I'll peek at the time. Okay, great. Find 2 3x3 matrices with all non-zero entries that commute. So no entry of A or B should be equal to 0, all right? In general, AB is not equal to BA. So probably most of the time, any random choice is not going to give you something commutative, I would guess, unless you're lucky. Okay, so you might have to think about some particular kinds of matrices and then simplify some of the terms even further. All right, great. So in other words, so if I read this now, the first time I saw that, I thought that it should say, or I thought that it meant that A was not equal to the 0 matrix and B was not equal to the 0 matrix. But now if I read it, I understand this to mean don't choose the identity matrix as well, right? Because that has some zeros in it. Okay, good. So you got a little bit of work to do in that. It's not totally trivial. Okay, question 5. Now, this is where things start to get a little bit more involved, but it's still easy. And maybe I need to move the chat. I think that's probably okay. Okay, in chapter 3 of VMLS. So that's a book that is, well, it's basically required reading for your course, right? Okay, so there are definitions for AVG, RMS, and STD. There's also a derivation of this identity for any vector x that STD squared is equal to RMS squared minus AVG squared. And then the question here is to describe the steps of the derivation of this formula in detail, okay? So I happen to have the steps of that formula, but also I have the definitions of those functions themselves. So I'll pull that out for you. And I'll cover up the details of the rest of what I've done here to make sure I understand it. Okay, so I think someone in the chat earlier asked to zoom in. This is a little bit hard to see. So I'll try to zoom in a little bit without it. Well, I'm just going to stop playing with that. So it either goes too far or too far out. Too far in, too far out. Okay, so here are the definitions, right? So AVG is just as the name suggests, the average. Okay, so yeah, so the vector x has n entries, x1, x2, up to xn. So if we add all those up and divide by n, then we have the average of the entries of x. Okay, RMS, I can't think off the top of my head what that refers to, probably because I'm not a statistician. But we have the sum of the squares of the entries, and then we take the square root, and then we divide by the square root of n. Okay, so if you look carefully, well, that's just the norm in the numerator, right? That's the norm of the vector x, and then that's the square root of the length. All right, sure. Okay, STD. So I'm guessing that means standard deviation, and somebody in the last session nodded yes, so that was good. All right, but also nicely, this one is represented as a norm as well. Okay, so we have x minus the average, and then we take a square of that, sum those up, and take the square root. So that's a norm of x minus, well, the average times a constant vector of 1s inside that square. And we take a norm of that and divide by the square root of n. I think if I've thought about that right. Okay, so next. So I'd state here, X is an n by 1 matrix, okay? Just so we're clear, right? It's a column vector, all right? But that helps you think about how these products are done. All right, so sure, that's just rephrasing the question. Now here's the derivation that you're given, which is in that book. Okay, so it's got, what, 5 lines? So this is not very much work for you, but you've got to describe the steps of the derivation in detail. Now, the first thing you notice is that this involves norms and vectors, right? Whereas the definitions up here, they've got sums and square roots, okay? So your task is to explain these things in here in terms of how do these relate to sums, right? And then explain how you get from this step to this step to this step, and so on, both in this way and possibly additionally in terms of the sums and the definitions. Okay, so I would, if this were me, I would do 2 proofs, all right? So here's proof 1. And then proof 2 is where you take these definitions and you deal with the sums and expand this out in terms of those sums, all right? You should be able to get this in the end. And that might help you more easily explain what's going on in these steps. But let's just have a look at one particular term, okay? So here we have a norm squared. This out the front is a scalar, 1 divided by n. Okay, here we have the vector x minus something times a bold 1. Now that bold 1 apparently is a statistical common thing to write, but it just means the column vector having all 1s in the entries, okay? Okay, so this inside the round bracket there, that is the column vector with 1s in the entries transposed. So that is now a row vector with 1s in the entries. And it's multiplied by the column vector x. Okay, so think about what that does. When you take that product, it simply adds all of the elements in x. Okay, so it's a sum of all of the elements in x, and you could write that in sigma notation quite easily. And then you're dividing that by n, but you could put that division in front of a sigma notation, okay? And you could easily relate it back to those. All right, so now I don't want to explain any more there because in explaining more, I'm doing the problem, okay? So I'll move on and talk about question 6. Now, since it's only 6:39 p.m., I'll probably have more time to spend on question 6 than in the last session. So that might be helpful for you. All right, but just let me have a moment here to stretch my neck, getting a little sore. Okay, I'm good. So let me find the next problem. So the next one says, I'll cover up everything else. Do exercise 3.26 from page 67 of VMLS. So that's the same book as the one above. Okay, so what is this problem? Well, I have it right here. Okay. And let's carefully read through it. Okay, so we've got italics, time series autocorrelation. So that's just a title of the problem, okay? So you can tell by that it's going to be a nice problem. Maybe I can zoom in a little bit. All right, good. Okay, so I'll cover up, because if you're like me, it's hard to look at a lot of text at the same time, right? I think I must have a little bit of dyslexia. So I like to cover things up so I can take in that information carefully, all right? And it's probably better for you guys to look at too. Okay, so suppose the t vector x is a non-constant time series. So now look at this, t vector x. So that is referring to the vector x having t entries in it, uppercase T entries, right? So that's just the entire period of time we're considering. All right, so it's non-constant, it's a time series. So what does this mean? It's just values of a measurement of something over a time period where each entry is at a particular time. All right, now a good example I can think about would be, if you like to look at prices of something, I don't know, let's just talk about the price of US dollars, for example, priced in Australian dollars, why not? Most people like to look at that the other way around anyway. So you might see some green and yellow candlestick pattern, right? Okay, so you could instead represent, so the price of US dollars in terms of Australian dollars at the close of the market. Does that happen with dollars? I don't know. Does the market close? I don't know. Anyway, let's pretend it does. So you might, you would have a number that corresponds to the price, say, at a particular time. And every entry of your vector would be a price at the same time, right? So between entry 1 and 2, that would have a particular time corresponding to that, and that would be the same amount of time between entries 2 and 3. Okay? Just to be totally clear. All right. So that's going to be denoted with x subscript little t. Now all we're doing is indexing, or pulling out the tth entry of the vector x. Okay, so the value at time t, lowercase t. Let mu, and mu is equal to the column vector of 1s transposed times x, all divided by uppercase T. Let this denote its mean value. Now you can see by looking at that notation and knowing about the previous question that is multiplying 1 times every entry and adding all those together and then dividing by the length. Okay, so that is in fact the mean. All right, the autocorrelation of x is the function r of tau. So here we have a new letter tau. And that is defined for tau equals 0, 1, and so on. So this is defined as the correlation coefficient of the two vectors. Now this correlation coefficient is particular to this book. And I'll come to that soon, okay? But first I want to talk about these two things, because when I first saw these, having not looked through the entire text, well, I didn't know what they meant, okay? So let's just describe that. Okay, so first of all, I'll give a definition. Let's imagine we've got two vectors, A and B. All right, now ordinarily this kind of notation would refer to the inner product, right? Dot product. But in this context, it doesn't mean that. Instead, this means if A is, say, I'll put a bigger bracket here, and let's go A1, A2, A3, and let's imagine that the vector B only has two entries. Let's say it's B1 and B2. Okay, so this is going to mean, and I need a lot more space, basically glue these two together, starting with this one. Okay, so it's like concatenating if they were two rows. But we're just taking this, and it'll make sense once I draw this. So A1, A2, A3, B1, B2, and there you go. That's what this means, okay? All right, good. So now we can talk about this. All right, so here, and I think I've got enough space here on this side. Okay, so mu bold 1, and I'm going to make that double struct so I convey that I mean that it's bold with a subscript tau. All right, so this one, as you know, is a scalar, and that's just the mean. All right, this one is a vector containing ones. And so what is this? Well, it's a scalar product. Scalar times vector. So we have mu in the first entry, we have mu in the second entry, and then we have dot, dot, dot. We have mu in the last entry. Okay, and how many of these are there? Well, there are tau of these. Okay. Now, tau could be equal to 0. And if tau is 0, then we don't really have anything. Keep in mind that there's no such thing as the empty vector, right? Because in a vector space, you need to have a 0 vector, right? So this is somewhat of an abusive notation, but that's okay if we understand what we're looking at, all right? So the empty vector in the context of doing this will mean you're not gluing on anything to X, right? That would be just, in that case, it's just X. Okay, so that's what that means. Now, so what we're doing is we're gluing this one onto X at the end. And in this second one, we're gluing X onto mu, but X is at the end, and the vector with mu's in it is at the front, okay? So then the length of both of these are uppercase T plus tau. Okay, so length, I'm writing where you can't see it. I'll try to, length of X mu bold 1 tau equals T plus tau, all right? And obviously, if you swap that around, it's tau plus T, which is T plus tau. Okay, good. So now that we know those, we need next the definition of R of tau. Okay, so basically R of tau is equal to rho of, say, P tilde, Q tilde, which is equal to P tilde transposed Q over the norm of P tilde times the norm of Q tilde. All right, and in this case, I put P equal to X and mu on tau, Q equal to the other one. And what am I missing? The tilde. Okay, now the tilde is just, if I remember right, yeah, I think so, is to subtract the mean from every entry, okay? So in other words, X tilde is equal to X minus, I'll just write mean of X times 1. And here, I'll put an uppercase T, because this should have T entries here when I define that, right? Okay, so good. Now you have all the definitions. The rest is actually easy, right? It's a bit of work, but it's easy, right? This is the part that I had trouble with. The rest is actually easy. So, and what do you know? It's 6:51, so we're out of time because we're going to finish at 10 to the hour, all right? So the first session was 50 minutes. Let's let this session be 50 minutes too. Okay, I'll hang around if you got any questions though. All right? Yes?
in the question, I think it's question 1.
Okay, question 1.
Question 1.
Hang on, I put that away, so I'll find it and I'll pull it back up.
That's okay. The question B. Do we need a print screen of the Julia or just write down the code?
All right, so the question was for everyone listening elsewhere. So the question is, can you print screen, or do you need to include your Julia code? Is that right?
Yeah.
Well, I think you're going to include your Julia code because, and you might need to ask Yoni about this, right? No, but what I'm thinking about is question 7, right, which is surely a little bit more involved than part B of question 1. So let's read question 7. Implement a Julia function that receives 2 matrices, A and B, and implements the product AB if they can be multiplied in this way. Because sometimes, you know, AB is not defined, right? So, all right, so let's read on.
So when you use a zip file to after the PDF
A zip file after the PDF?
for the advertising.
Well, were you told that?
The code, the Julia code, should we just save the code and after the PDF file?
Well, I don't know yet. I want to ask you, did Yoni tell you that you should zip up the code?
I don't know.
No, you don't know. So that's a pure question. Okay. So I'm trying to decide what the best practice should be at this point, all right? Because basically I know that this one will be a little bit involved. And if I look at this one is probably a Julia question too, right? Because if I remember last week, I thought we were dealing with random matrices with entries belonging to 1, 2, and 3. Okay, so I have a feeling that this is a Julia question. Now, I didn't actually read this far yet, or I haven't read this far yet to speak correctly. So I think that you could probably submit your Julia code, and I don't think you would have to zip it up because I don't think it's going to be too long unless you have a lot of data coming out of it, in which case you might need to zip it up, all right? But we'll see. I mean, that's a couple weeks away. Yeah, so
Our voice.
so that says that you could probably do this one here in the same Julia notebook or IP something file, all right? You could probably do it provided you're careful to clear the memory after that. Yeah, you don't want to be using the same calculations from that one down in this problem, okay? But I mean, since this B is such a simple problem, I think you could probably include a screenshot. So honestly, I don't know. I think both ways would be acceptable. Yeah. All right, any other questions? No? All good? How about you in the back? Happy? You look happy. Yeah, I can see in your eyes, even though you're wearing a mask. But, you know, you can see happy eyes, so yeah. All right, thanks very much, guys.
Thank you.
See you next time.
然后这个加任何加 S， 就是你那个来过。语法是什么？哎。